Hi! In this work, we propose a new Focus+Context visualization technique for the inspection of simulated black oil reservoir models. Simulated reservoir models are used in the oil and gas industry to predict and plan the exploration of petroleum fields. Reservoir engineers try different well arrangements and exploration strategies to maximize the economic return of the reservoir. We are interested in helping experts to better understand the physical phenomena around injector and producer wells. For this reason, we propose the following cutaway visualization, where users can select one or more wells as objects of interest to apply the cutaway. A well here is represented by cylinders that follows the well trajectory. Our cutaway has two visualization modes, a view-dependent mode where the cutting surface can be updated by controlling the cut aperture or by changing the camera position, and a view-independent mode that, when activated, freezes the cutaway surface generation, and we can change the camera position without modifying the cutting surface. This provides us with motion parallax, which helps to infer the depth of the well in the reservoir cutaway. In both modes, we can enable the wireframe for the reservoir external faces and for the cutting surface geological layers. In the view-dependent mode, we can change the selected wells to apply the cutaway. In our view-dependent cutaway, we represent our cutting surface by a depth map and an intersection map with the dimensions of the frame buffer. The depth map is obtained by using the backface depth of the selected wells as input to compute a distance transform with the jump flooding algorithm. The intersection map represents positions of the cutting surface depth map that are inside the reservoir cells. This is computed with an efficient point location algorithm in GPU. We render our model applying the cutaway by comparing z-values from the depth map with the reservoir model hull fragments depth. If the model fragments are between the camera and depth map, we check if the intersection has occurred and use the assigned color if it does, otherwise we discard the fragments. Model fragments that are not between the camera and the cutting surface depth map are drawn as they are. After rendering the reservoir cutaway, we can draw the select wells to complete our visualization. During the view-dependent cutaway visualization, we can enable the view-independent mode. We want to change the camera position to better inspect the cutaway, but we don't want to change its shape with the camera in motion. Thus, in the view-independent mode, the depth map and intersection map are no longer updated, and we use the ones set in the last draw. Then, we render the cutaway cutting surface with the relief mapping algorithm, using intersection map to assign the colors to the cutting surface. Please check our papers for more details. We also propose the box-shaped cutaway. This kind of cutaway shape is important because it maintains the natural alignment of geological models. We are still using a depth-based cutting surface, but we have built this one with an aligned bounding box of the select wells. After applying the cutaway to the reservoir model, we also draw the reservoir bottom layer immediately below the selected well. Despite our initial goal to present a visualization technique to inspect the vicinity of wells, we ended up with a more general visualization. We can compute the cutting surface for other objects of interest. For example, here we used a set of cells as object of interest. We evaluate the performance of our visualization with 5 reservoir models, with cell counting ranging from 30,000 cells to 16 million cells, as can be seen in Table 1. Our cutaway algorithm shows a good performance even for a large model with 16 million cells. We also evaluate the performance of each phase of the view-dependent cone-shaped cutaway, with increasing size for the cutting surface, as seen in Table 3. As the cut size increases, we observe that the intersection map is responsible for the majority increase in the cost of the visualization. To conclude, we have the following contributions. We have built a new visualization to inspect black oil reservoir simulation results. A new efficient algorithm to render cone-shaped cutting surface based on a point location procedure, capable of handling objects of interest of any shape. A new box-shaped cutting surface construction algorithm using a reservoir layer as the bottom wall, and an efficient view-independent cutting surface construction based on the relief mapping algorithm. Thank you for your time.